Hello, everyone. Are you guys able to hear me?
Yeah,
Okay, we'll just wait a few minutes so that we can get started. Did the meeting ask you to enter the passcode or?
yeah, it asked for a passcode.
Hmm, Okay, so I think we can get started now. So, hello, everyone. My name is Fahad, and I'll be your TA for EECS 1028 Discrete Math course. So the tutorial runs from 5:30 to 7:30, although we will finish earlier if there are any questions that you guys have, so we can finish earlier. And if I get disconnected because of unstable connections, so please feel free to rejoin. And I think we can get started now. If you guys have any questions, so feel free to ask me over the text, or if you would like to speak up. So the exercises we will be covering in this tutorial will be from exercise 1.1, 1.2, and 1.3. So we will be covering three exercises, although the instructor have taught you until 1.5. But in this tutorial, we will be covering only up to 1.3. So if there are any other questions, if you guys have any questions, so I can take, otherwise we can get started. Okay, so no questions. All right. Okay, so I hope everyone is able to see my screen. So if you guys can see my screen, just please confirm that.
Yes, we can see.
Okay, all right. So I have already written down a few questions from the textbook, and the question number is also written just for the reference. I will be solving some of them, not all of them. If, as the instructor mentioned, that if you guys have any questions at request, I can take on before 24 hours. So just feel free to email me those questions, and I will cover them up in my tutorial. So the first question is from exercise 1.1, and the question is, which of these sentences are propositions? What are the truth value of those propositions? So Boston is the capital of Massachusetts. So for this one here, so proposition is a statement which is either true or false. So since this is a statement which is either true or false, so we can say that yes, this is a proposition. And then we also have to determine the truth value for these propositions. So this is also a true. This is sort of like based on some general knowledge question, but we won't be judging your general knowledge in this course. We will be only judging the course material taught in this course. So if you don't know that Boston is the capital, so that's all right as well. So the second one is Miami is the capital of Florida. So this one is also a proposition because it either evaluates to true or false. So therefore it's a proposition and it is the capital of Florida. Therefore, this is the truth value of this proposition. The C part here is 2 plus 3 equals to 5. So this here is also a proposition because it is either equal to 5 or it is not equal to 5. So there are only two answers to this question. So 2 plus 3 equals to 5. So therefore this is a proposition and the truth value is true. So part number D here. So we have 5 plus 7 equals to 10. So here, this is a proposition, but the truth value for this question is false because 5 plus 7 is not equal to 10. And then we have the part number E, x plus 2 equals to 11. So here, this is unknown because we don't know the value of x. So if x is 1, then 1 plus 2 is not equals to 11. X can be any number, so therefore we don't know what the actual value of x is. So therefore we cannot say if this is equal to 11 or not there. So therefore we will say that this is not a proposition. All right, so any questions regarding this question number one?
Yes, please. I'm wondering why A and B are true.
Why A and B are true?
Yeah.
Yeah, because these are proposition values.
Mm-hmm.
Yeah, so it either evaluates to true or false. So this statement, this is the proposition is a declarative statement, so which is either true or false, right?
Yeah,
So
exactly.
yeah, so Boston can either be the capital or it cannot be a capital because
Yeah.
the value Boston is a known value. It is not, for example, X is the capital, right? So if it is X is the capital of something, then we
Mm-hmm.
cannot decide that if it is true or not. But because we know that the value of X is Boston, so therefore we can say that this is either true or false.
Okay, that makes sense. Thank you.
Any other questions before we move on to the next one? All right, if no questions, let's move on to the next one. So in this question, what we have to do is we have to find the negation. Negation is basically the opposite of some statement. So here we have Linda is younger than Sanjay. So the negation here will be that Linda is not younger than Sanjay. Or there can be another way to say that. For example, I can also say it like it is not the case that Linda is younger than Sanjay. Okay, so just like in English, we have so many ways to say one thing. So likewise, we can either put it like Linda is not younger than Sanjay, or we can say it is not the case that Linda is younger than Sanjay, or something of that nature, which basically depicts that this is the negation of the statement. So the next one is Mai makes more money than Isabella. So we can say Mai does not make more money than Isabella. Mosh is taller than Monica. We can say Mosh is not taller than Monica, or we can say Mosh is shorter than Monica. The next one is Abby is richer than Ricardo. So Abby is not richer than Ricardo. So as you guys can already see that this negation, finding a negation for a proposition is not really a big thing. So if you guys have any question for this question number 3, then we can move to the next question.
I have a question.
Yes.
So for the question number 3, if we exchange the subject, like we say like Sanjay is younger than Linda, would that be any question?
Yeah, so here, so we have this, so Linda here is our premises, and then Sanjay is the hypothesis. So we are saying Linda is younger than Sanjay. You
Mm-hmm.
want to say that Sanjay is younger than Linda. So this is like a proper negation as well, but because this is not very clear in terms
Mm-hmm.
of like putting the not word, so therefore you can use that as well, but if you want to be more clear, then I would suggest you use words like not, because
Oh,
negation is all about that word,
all right, thank
just
you.
because it makes the statement clear. But
Okay, thank
like I said, you can also use your words like it is not the case that Linda is younger than Sanjay.
you. All right, thank you.
Any other questions? Right, let's move on to the next question. So some more negation question. So we have what is the negation of each of these propositions? So my has an MP3 player. So my does not have has an MP3 player. There is no pollution in New Jersey. We can say there is pollution pollution in New Jersey. So 2 plus 1 equals to 3. So this is also a statement, equally valid statement. So we can say 2 plus 1, and then we will use the not equal sign. So the not equal sign. So I'll just write it because I don't have the key for that. So not equal sign. I'm sure everyone knows the not equal sign. So we can use that sign here. So 2 plus 1 is not equals to 3. And then we have the summer in Maine is hot and sunny. So the summer in Maine is not hot. And also you have to be careful here. We are using the word and. So whenever we have the words like and or the word or, we also have to negate that as well. So if it is and, then we will make it an or. But if it is or, then we will make it and if we are taking negation. So here this will be converted to an or. So the summer in Maine is not hot or sunny. Or just to be more clear, you can say or it is not sunny. Any questions?
Yeah, I have a quick question. Could you say the summer in Maine is not hot and is not sunny? And it is not sunny?
And it is no, we cannot say, because here we are basically taking the negation of the whole thing. So according to the De Morgan's law, which we will be studying later on in exercise 1.3. So according to that law, so we also have to negate this operand sign, so and or. So we also have to invert those signs as well. So we cannot say the summer is not hot and it is not sunny. So we have to say or. So we also have to negate the and sign.
Okay, thanks.
Sir, if you say the summer is in Maine is not hot, can you say nor, like NOR? Nor it is sunny.
Yeah, so basically here is nor hot or it is nor sunny.
No, like the summer in Maine is not oh yeah, like that. But like, does it work?
I think because not and nor, they have different meanings in English language. So therefore, this may not be a very fitting word here. I think not will be a more fitting word here.
Oh, okay, okay, thank you.
Yeah. All right. If no
If
more,
we say that, sorry,
yeah, go ahead.
what if we say like the summer in May is neither? Oh, never mind. Actually, doesn't make sense. Yeah.
I'm sorry, I'm not able to hear you clearly.
No, it's okay. I got it. It just yeah, I got it.
Are you sure?
Yes, I did. Thank you.
Okay. Okay, if no more question, let's move on to question number 7. So we have what is the negation of each of these propositions? So we have the first one here. Steve has more than 100 gigabytes free disk space on his laptop. So just like we did earlier, so Steve does not has more than 100 gigabytes free disk on his laptop. The next one is Zash blocks email and text from Jennifer. So here you have to be careful about the N word. So we will say Zash does not block emails, or so we also have to revert the N to or texts from Jennifer. We have 7, and this dot operator, it means multiply in computer science. So here we have 7.11.13, and then here if we have to revert this, we take the proposition negation for this, and then we will convert this equal to sign into the not equal sign. So I'm just writing it down. You have to basically put that sign instead of just writing this. Okay. And then we have Diane rode her bicycle 100 miles on Sunday. So Diane did not ride her bicycle 100 miles on Sunday. So any questions here?
So the negation of and is or.
Yes, the negation of and is or, and the negation of or is and. So if it is or, then we convert it to and when we're taking negation, and then we do the vice versa.
Okay. Okay.
Yeah, so since this is a very introductory exercise, we will be putting those knowledge in practice as well by truth tables and also getting more deeper into this. Okay, any other questions?
Hello. In question A, is it possible to use Steve has less than or equal to 100 gigabytes?
Yes, because the point is to say that it doesn't have more than 100 gigabytes. Steve can have equals to 100 gigabytes, or Steve can have less than 100 gigabytes, but he cannot have more than 100 gigabytes.
Okay.
Okay. Okay, moving forward. Question 9. So this is a big question. So suppose that during the most recent fiscal year, I'll just give you guys a few minutes to read the question and understand the subtasks here. All right. So we will be doing part number A and part number C only. So for part number A, so we have this Quicksort Media had the largest annual revenue. What we are really trying to do here, we are trying to estimate the truth value based on the knowledge given to us in the question. So based on the question, we see that this company here, Quicksort Media, it does not have the largest annual revenue because there's another company with the name this Acme Computer, which has a bigger revenue. So therefore, the truth value for this will evaluate to false. So this was a long question, but with a short answer. And then part number C, here says Acme Computer had the largest net profit. So if we read the question carefully, we know that it does not have the largest profit because there is another company, the Quicksort Media, which has a $13 billion net profit. So therefore, this will be false. However, we have this or sign here, so I'll just put or here just to break it down for you guys, but you can just write the direct answer as well, but I'm just explaining here. So here Quicksort Media had the largest net profit, so which we just said that it does. So we have false, a statement which is false, and it is ORed with a statement which is true. So false or true evaluates to true. Therefore, the answer for this statement, the truth value for this statement here is true. You can just write down true, or you can, if you want to break it down just to be more clear, you can do it this way.
Hello. Can you hear me? Or
Yeah, I can hear you.
okay. So, how do you know like false or true is equal to true? Is it based on the truth table, or like how do you know is it if it's exactly true?
Yeah, so this is based on the truth tables. So there are truth tables for the and, for the or, and then we have the different operands as well, like the biconditional and the other ones. So you probably have to memorize those. These are not very hard ones, but those are the basic ones on which
Right.
like the other yeah, the practical questions will be based on. So you guys are expected to have them memorized.
Also, I was having a hard time coming into the Zoom session. So, can you provide the passcode to the professor so he can add that to the e-class link? That's why there's only 13 people in the class.
Yes, thank you for raising that question. So I already provided professor with the password, so he will update it on the e-class.
Oh, thank you.
So just wondering, how did you guys enter the meeting? Do you guys have like a WhatsApp group or something?
No, it's the Microsoft team.
Oh, the Microsoft team. Okay, thank you for doing that. I have let professor know about this issue, and he will update it.
Oh, thank you.
Okay, any other questions regarding this?
Could you please do E?
Go ahead.
Like, could you please do E for like the question number 9, sub question E?
Question part E.
Yes, please. Hello?
Yeah, hello.
Oh yeah, I was asking about question like the part E. Could you please do that?
Yes, if you guys have any, just like I mentioned earlier, so if you guys have any special requests, the questions you want me to solve, just please email me those questions at least like 24 hours so I can, just skim through those questions and understand them.
Okay.
Okay. All right. Let's move on to question number 11.
Sir, can I ask a quick question?
Yes, please.
So, uh, so like, I can send you any question. It doesn't matter if it's even or odd, right?
Yes, it doesn't matter as long as it's included in the course curriculum.
Oh, okay, yeah. Cause I did a couple of even problems and I'm not really sure about it. So I'll probably ask next week.
Yeah, so the next week we will be covering different exercises. So make sure that your questions are related to those exercises.
Okay, thank you.
All right. All right. Let's move on to the next question. So question number 11. So we have these propositions which are represented by some proposition variables. So for example, this variable here, P, it represents swimming at the New Jersey shore is allowed. And then we have this Q variable, which represents sharks have been spotted near the shore. So we have to express each of these compound propositions as an English sentence. So this is part number A we are doing here. So this negation sign here represents the not symbol in English. So this is the negation sign, and then we have the negation of Q. So we have this statement Q, shark have been spotted near the shores. We have to take the negation. So what we do is sharks have not been spotted near the shore. Okay, just taking the negation for the Q statement represented by the variable Q. The next one is part B. So we have P, and then this symbol here represents and in English language. So we just say, we take the statement represented by P variables, which is swimming at the New Jersey shore is allowed. So this is the statement represented by variable P, and then we have this and operator represented by the word and then we take the Q, which is sharks have been spotted near the shore. Right, questions? All right, part number D. So this sign here, this means if this part here, then this part here. So this part, this side, it's called the premises, and then this is the hypothesis. So we have here, if swimming, the statement represented by the variable P, if swimming at the New Jersey shore is allowed, then sharks have, so we take this negation sign into English word, which is represented by the word not. Then sharks have not been spotted near the shore.
If you don't mind me asking a question, can I ask?
Yes.
So I think when it comes to certain statements, it's hard to like so for example, this one's a conditional statement. So how do we know where we have to add if and then? and when it comes to writing the when it comes to writing the statement down, because it has to make sense, right?
Yeah, so in some English phrases, when we have to convert a propositional statement to an English sentence, sometimes it doesn't make sense. But based on the proposition that is given to us, so for example, here we have this P. So what I did is I just take the P part. So swimming at the New Jersey shore is allowed, right? And then
Right.
I put if word in front of it, and then this sign here I replaced it with
Implies.
then, right? So this
Yeah.
order usually tells you like the way it's ordered. So it usually tells you how to put your English sentence together, even though it makes sense or not. But usually it will make sense because they will be given you in such an order.
All right. Okay. Right. Right. Okay. Thank you.
All right. So we have part number G here. So we take P here, which represents swimming at the New Jersey shore is allowed. And then we have this biconditional sign, which in English terms means if and only if, also represented as IFF. So swimming at the New Jersey shore is allowed. We replaced this biconditional sign with if and only if sharks have not, we have to make sure we add the word not because of this negation here. Sharks have not been spotted near the shore. So swimming at the New Jersey shore is allowed if and only if sharks have not been spotted near the shore. So as you guys can already see that this makes sense because this is given you in such an order that will make sense. But if I revert the order, it won't make any sense, but it will still be a valid representation in English language for that proposition. Moving on to part number H. This is a little bit trickier and a little bit longer as well. So we have sharks have not been spotted near the shore, or I'll just highlight those words, or swimming at the New Jersey shore is allowed. And swimming at the New Jersey shore is not allowed.
I have a quick question.
Yes, go ahead.
So this one's kind of confusing to me. Did you like look at the order? Do we have to consider the order of the proposition? So did you start off with the with a P or not Q first, and then you went to negative to not P? Does the order matter in this case? That's what I'm wondering.
Yes, the order matters. Yeah.
So the one with the parentheses comes first, and then.
Yeah, so later on we will also study the different rules we have. So for example, we have the Morgan's law, we have absorption law, we have these different kinds of law, which will help us to evaluate these different orders and how we can manipulate the order as well. So we will study this ordering of the variables there. So in here, we are taking this statement P, the statement represented by P, we are applying the negation for that. And then I took the inside one. So this one here, swimming at the New Jersey shore is allowed, and swimming
Okay.
at the New Jersey shore is not allowed.
So you started off with the with the negative Q, right? No, not Q, right?
With the not Q, yeah. So we have this law here. So when we open this up, so we have this statement here, negation P, and this in the bracket we have P or negation of Q. So when we apply the rules to this statement, so this statement open up to this English sentence.
Hi, can I ask a question real quick? So earlier you did a negation of and it became or. So what if you were to do a negation of an implication statement?
Sorry, repeat the question.
So earlier there was a statement where you did negation of and it became or. So what if
Yes.
you were to do the same with the implication instead of and the implication?
Right. So if we apply negation to implication,
Yes.
yeah. So for example, here, I think we have an example later on. I will teach you there because I have to share a different screen for that. So I will share it at that time. How about that?
Okay. All right. Thanks.
All right. Yeah.
I have a question. Why didn't we start with not P or on the part H?
Sorry, say that again.
Why didn't we start with the not P? Like say swimming at the New Jersey shore is not allowed, I think, and then go on with the other P or do I
So
make sense?
why did I write it this way?
So Amika, okay. So the way I think you did it, you started with the not Q, right? And then yeah, with the not Q and O. So you started from the back. Why couldn't we start with not P?
Yeah, so here we have for the part number H, this is a little bit trickier because there can be different ways of expressing it. So we can apply some law to it, we can open it up, and we can represent it in a different English representation. So this is one of the representation. If you have any other representation, I can verify that for you. If you can just email me that.
Okay.
All right. Okay, let's move on to part number 13. Okay, so for the question number 13, we have these propositions are represented by a variable P and Q. So we have to represent it in this propositional statement form. So the first one is it is below freezing and snowing. So we will say it is below freezing. It is represented by the variable P. So we take the variable P and then we put on the and sign here, and then we have the variable Q, which represent it is snowing. So P and Q will represent this English statement here. Secondly, we have for the part B, we have it is below freezing but not snowing. So for it is below freezing, we use the variable P, but it is not freezing. So we use and then we use the negation sign. So I'm just writing negation, but you have to use the negation sign, which is right here. Okay. So P and negation of Q, which will represent it is below freezing but not snowing. For part number
Okay, I
C,
have a question.
yep.
For B, why do we use and while there is no and in the statement?
Yeah, so here how the sentence is structured, it is saying but, right? It doesn't have to explicitly say and not snowing. It uh, sort of represent the same thing, right?
Yeah.
So it is it's a condition that it is below freezing but not snowing. So it is emphasizing that it is going both ways, right? So you have to use the word and. We cannot use the word or for this, right?
Yeah. All right, thank you.
Yeah. So for the next one we have it is not below freezing. So we will say negation P, and we will use the word. We have the word and here, so this is very clear that we need to use the operator and it is not snowing, so we will again use negation and then we will use Q, so which represent it is not snowing. Part number E, if it is below freezing it is also snowing here. So here we have the words like if, then we are basically satisfying another condition. So we have some precondition and which basically promises us some result. So if it is below freezing, so only then we will see that snowing, it's snowing. So here, because we have an if then sort of promise here, then we will use the conditional operator for it. So we will have this P, and then we will use the conditional P, if P, then Q. So if it is below freezing, then it is also snowing. All right, so questions? Okay, no questions. Let's move on to the part number A. Let's do part A, C, and G only. So we have these variables P and Q representing the statement here. So the first one here is you do not drive over 65 miles per hour. So we have this you drive over 65 miles per hour statement represented by P. All we have to do is take the negation for this statement. So this is easy. Negation of P. Then we have part number C here. You will get a speeding ticket if you drive over 65 miles per hour. So here we have to use both of these variables, P and Q, because as represented by the English sentence, we will require both of those. So here we can already see there is a if-then sort of promise. So this sort of clues us that we need to use the conditional operator. For the part number C here, we are getting a speeding ticket only if we drive over 65 miles per hour. So if you drive over 65 miles per hour, then you get a speeding ticket. For part number G, we are saying whenever you get a speeding ticket, you are driving over 65 miles per hour. Here we also see sort of the same uh, if then behavior, but in a different reverse order, because you are getting a speed ticket only if you are driving over 65 miles per hour. So we will say whenever you get a speeding ticket, so we have this Q, we have this sign here for the conditional. You are driving over 65 miles per hour, represented by the variable Q, P. So whenever you get a speeding ticket, you are driving over 65 miles per hour. So in order to determine the propositional statement for an English sentence, you need to basically look out for some words in that English sentence. So for example, we have words like whenever, we have words like if, then, we have words like and, or. So these ones are mentioned in your slides. For example, for the conditional word, there is some words which basically sort of hint you that you need to use this operator as compared to, for example, biconditional. So just make sure to go over the slides, and this will ensure that you're using the right operators.
For B, 15B, would it be B and negation Q?
P and negation Q.
Yeah, B. No, P. I mean, but
Yeah,
P
for the B
and
part.
negation Q for B, for
Yeah,
15B.
yeah, so for the B part, it will be P and negation Q, because this is, we have this but sign here, which represents the and in English. Oh, sorry, and in the and operator in propositional statement. And then we have this not, we have to take the not for the Q part.
Okay, got it.
Okay, any other questions?
For part E, is it an implication there?
Sorry, which part?
Part E, is there an implication there? Because there's sufficient.
Yes, so this also, yes, part E also represents implication.
Uh,
Yeah, so here we have the word sufficient, right? So this basically tells us that we have to use the word, the this implication there instead of the biconditional or and or the other operators. So my suggestion will be to basically read the slides if you're unsure which word, which operator to use. Any other questions for this exercise? All right, if no question, we can move on to the next exercise, which is the exercise 1.2. And here we have this question, which before we do that, however, let's take a quick 10-minute break. So because we're already in the middle of the tutorial, so if you guys want to maybe grab some coffee, then we can connect back in 10 minutes. So, but if you can just remain on the line, just stay connected, and we'll catch up in 10 minutes. All right, let's get started. So this is exercise 1.2, and the question number 1. So here we have this question: you cannot edit a protected Wikipedia entry unless you are an administrator. So express your answers in terms of the proposition variables. So here we have this keyword here. So unless, so which represents the use of the implication. So we will be using implication to represent the statement here. So we will use this A statement, which is you are an administrator, and then we imply that statement represented by E, which is you can edit a protected Wikipedia entry. So if you are an administrator, then you can edit a protected Wikipedia entry. So this basically is represented in this um, proposition statement. All right, let's move on to question number 7. So we have this express the system specifications using the proposition P. The message is scanned for viruses, and the statement represented by Q. The message was sent from an unknown sender together with logical connectives. So first we have this, the message is scanned for viruses whenever the message was sent from an unknown system. So this one here will be represented through implication again. So we have Q, which represents the message was sent from an unknown system, which implies that the message is scanned for viruses. So here, the message is scanned for viruses whenever the message was sent from an unknown system will be represented using this proposition statement. Or we later on when we will be studying the laws on these operators, so we will find some ways to open this up or represent it in terms of like the other logical operators. So for example, I can represent this implication with negation of Q or P as well if I want to open it up. But for the time being, we will just stick to this, and later on we will find the more concrete implementation of this. The next one is, so it is necessary to scan the messages to scan the message for viruses whenever it was sent from an unknown system. So again, this one here will also be represented with an implication. So because it is necessary to scan the message whenever, and the words like whenever necessary, sufficient, if, then they will basically imply the usage of this conditional operator. So this Q implies P will be an equivalent representation of this English sentence. Okay, so moving on to this question here, question number 9. So we have this, are these system specifications consistent? So the system is in a multi-user state if and only if it is operating normally. So what we will do for this question is we will divide this whole sort of paragraph into different English sentences, the short English sentences, and for each English sentence, we will represent that with some proposition variable, and then we will compose a propositional statement using those variables. So for example, I can take, let's say for sentence, so I will say system is in multi-user state. So multi-user state, so I will say, so this is represented by, for example, P variable, and then we have I will have another one. So system is operating normally So I will represent this using the variable q, and then I will have another one, kernel is functioning. I will represent this with R. This is your choice for the variables, but this is like the standard for using variables like P, Q, R. And then lastly, I will have another statement represented by the variable S. So we have system is in interrupt mode, represented by the variable S. So now I have these statements here represented by these different variables. So I just picked up these statements based on this text here. So firstly, we have the statement: the system is in multi-user state if and only if it is operating normally. So in order to represent this one here, I will make use of the first one statement, so P, and then we will be using the biconditional operator here, because we have the word like if and only if. So this is a very strict condition here, so which we need to use. So biconditional P, biconditional Q. So this statement, the system, so this statement, the system is in multi-user state if and only if it is operating normally, will be represented using this P biconditional Q. The second one, which is if the system is operating normally, the kernel is functioning. We have all the variables we need to make up the proposition statement. So so here, if word basically represented, we need to make use of the implication. So if the system is operating normally, this is represented by the variable q, and then we have the implication sign, and then the statement represented by R will be used. So if the system is operating normally, the kernel is functioning. Number 3, we have the kernel is not functioning, or the system is in interrupt mode. In order to represent this, we will make use of the third statement here, represented by R. So the kernel is not functioning, right? So if the kernel is not functioning, we will negate this, negation of R. We take the negation of R. Again, you have to use the symbol for this and not just write it in English like myself, because I don't have the symbol here. So here, the negation of R, and then we have this symbol OR, which we have to represent with the symbol OR. Again, you have to use the symbol OR right here. And then the system is in interrupt mode, which is represented by this variable S here. So we will be representing it this way. So if the next one is if the system is not in multi-user state, then it is in interrupt mode. This one here will be represented with implication because of the words like if and then. This sort of hint us that we need to use implication. So we will take the negation. Negation of P implies S. Lastly, we have the system is not in interrupt mode. The system is not in interrupt mode. We have the statement here, the system is in interrupt mode. So this one is pretty straightforward. All we need to do is we take the negation of this variable S, so which will basically say that the system is not in interrupt mode. Questions?
Can you scroll up a little bit? Did we answer this question? Hello?
Yeah, go ahead.
So isn't the question like, are these system specifications consistent? Like, is it done? The question is it done?
Yeah, so here the question starts from within the quote marks, the quotation marks here.
Mhm.
So what we basically did, so we have this quotations here. So what we did is we took the text from here, and then we divided up into different sentences which we need to form up these conditional statements here. So these are basically just determined through the text, the English context that is given to us. All right, and then what we did is we basically form up the sentences which are helpful for us to make up those propositional statements. And then
Mhm.
we took this sentence, for example, this sentence, the first one, the system is in multi-user state if and only if, and we represented that English sentence by using these variables.
Okay. So is it consistent or not? Uh,
Right, okay. So you were asking if this is consistent or not, right?
Yeah.
Okay, so basically we have a definition for consistency here as well. I'll just read it out. So a list of proposition is consistent if it is possible to assign truth values to the proposition variables so that each proposition is true, right?
Yeah.
So here, since if and only if these truth values for the proposition variables account to true, only then we can say that this is consistent. So we see that for the first one here, we have this, the system is in multi-user state if and only if it is operating normally. We have we know that the system is, it's in multi-user state. There are some certain unknowns to it, right?
What did you say?
Yeah. So for example, if I assume, so assume, let's assume S is false. So for example, if I assume S is false, that the system is not in interrupt mode, right?
Mhm.
I assume that the system is not in interrupt mode, and then I'm assuming that Q is true, right? So if the system is not in interrupt mode,
Then the system is operating normally.
yes, if the system is not operating normally, then this will say that P is true,
Okay.
right? The system is in multi-user state. So therefore R is true. So
Yeah.
the kernel is functioning.
So it's consistent.
Yeah.
Okay. Got it. Thank you.
All right. Okay, let's move on to the last exercise 1.3 here. So this exercise basically involves use of the truth tables mostly. So what we will do is we will be constructing truth tables for these different proposition statements here. So firstly, we have this part A, so which says that we have this P and with this T here means true. So, and then this sign here, it means that it is logically equivalent to P itself. So here the P can either, because P is a proposition variable, so it can either be true or it can either be false, right? So there are only two possibilities for this. And then we have true, so true is going to remain true regardless of whatever it is. Okay, so if we take an and of P and T here, so if we take and of true and true, so true and true is true, and then false and true is false, right? So we have TF, we have this TF here as well. So this basically equals to this P itself. So therefore we can say that P and T is logically equivalent to P itself. Questions?
No, sir.
Yep.
Oh, I said no question.
Okay. Oops. Okay. All right. Okay. Let's move on to the part number C here. So we have P and false logically equivalent to false. So we have again. So we only have two possible values for P. We have true, false, and then for the false, it's going to remain false regardless. Okay. And we are basically going to AND this P and F. So C, true and false, as we saw above, it is true and false is false. And then we have this false and false is going to remain false. So here P and F is false and false. So which is basically equal to false itself. So therefore it is logically equal to false. Questions? All right, let's move on to part number E. So we have P or P logically equivalent to P. So we have to prove that P or P is logically equal to P itself. So we take P, P true and false again because it's a propositional variable, only two values possible. So P or P, if you take an or with itself, so for example, this is true, and then we have, let's say another one here. So P, true, and then false, okay? So true or true, it's going to remain true, and then false or false, it's false, okay? So P or P is either true or false. Therefore, it is equivalent to P itself because it is also true and false. So therefore, P or P is logically equivalent to P itself. Questions? Right, if no questions, let's move on to part number 3, question number 3, part B. So we have to use a truth table to verify the commutative law. So this here is a commutative law. It says that, so if we take P and Q, it is equivalent to Q and P. In other words, it just says that the ordering doesn't matter if it is just connected via AND operator. And then same thing for P or Q. So the ordering doesn't matter. Okay, so here we will do the part number B. So P, for P, we have 2 values possible: true, false, true, false. For Q as well, we have true, false, true, false. And then we have P and Q. So we will take true and true is true, false and false is false. Oh, sorry. Here we will do true, true. This is going to be false, false, true, false, and true, false, right? So we have this true and true is going to be true. And then we have true and false, it's going to be false. We have this false and true, it's going to be false. And then this is false as well. And then we are going to revert the order and add it together. So this is Q and P. So true and true is true. False and true is false. True and false is false. And false and false is false. Okay, so as we can see from the truth table that the truth values of these here, these two here, so they are equivalent to each other. Therefore, we can say that we have verified this via truth table that the commutative law holds. Questions? All right.
Sir, I have a question.
Yep.
Are we gonna go over the logic puzzle stuff?
Yeah. So these basically to evaluate the truth values, it is expected that you know at least how to and or the simple operators.
Okay.
So
Yeah.
yeah, and it just boils down to practice. If you have more practice, you are going to get better. So just practice more, and then probably it will be just on your fingertips.
Okay. Okay.
All right. Just give me a minute. All right. So let's move on to, let's give some question, and let's move on to question number 17. So here we have this again truth table as well. So we have to now verify the absorption law. So this absorption law here, it basically says that if we take P and Q and then we OR it with P, it's just P itself. So we just going to prove now. So we have this P, which can be true, 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 false, false. And then Q, it can be true, false, true, false. The way it's written so that we cover all the possible values. So we have the P and Q, which is going to be true, false, false, false. Now we have this P and Q, and then we have to OR it with this P. So P or these values here. So we take these values, we OR it with these values. Then this will give us true, true, false, and false. All right. So these values here, we just notice that this is exactly equal to these values, which is P itself. So in other words, we can say that this statement here is just equivalent to this P here. So we just proved the absorption law. Questions? All right, if no question, let's move on to the next one. So I just put down the truth table for the biconditional just to solve this question number 21 for you guys. Okay, so what we have to do is we have to prove that this is basically equivalent to this. In other words, the truth values for this one are same as the truth values for these.
Can I ask you a quick question?
Yep.
So I was trying this question, but I didn't use the truth table. I used the logic laws, constructing logic laws.
Yeah, that's fine as well, because here the question doesn't ask for like you have to use a truth table, right? So unlike for example here, right, it says by using truth table. So when it says that you have to use the truth table, then you cannot use the laws, you have to use the truth table. But for example here, it doesn't mention that you have to use the truth table, so you can either do it using laws or you can use the truth table. But because we don't have like a sufficient knowledge for laws right now, and it will be coming in next exercises, so we will be proving these statements using the logical laws.
Okay.
Okay, so here we have the true for the values P. It can either be true or false. True, true, false, false. And then for Q we have true, false, true, false. Now the biconditional statement here, so PQ, we can use this truth table to just get a quick so true, false, true, false, true. Okay, so this is going to be P biconditional Q will give us this value. You are again I'm not sure if you will be given the cheat sheet where these truth table will be drawn. You have to confirm this with professor. If he says no, then you will have to memorize it by yourself. Okay, and then what we do is we take the negation of this here. So negation of this, so false, true, true, and then false, right? And then here we are just taking the negation of Q. So we will say false, true, false, and true. Okay, and then what we are going to do is we take this P, and then we are basically biconditionaling it with this negation of Q. So true, we have this true, and then we have this false here. So true, false is false. We can use the truth table above to verify. We have true, true. So true, true is true itself. Oh, sorry, true. And then we have false and then false. So false, false is true. So false, false is true. And then we have this false and then this true. So we have this false and this true, which gives us false. False. Now, if we see that the truth values for this statement here, which is these false, true, true, false, are just the same as truth values for this one here, false, true, true, false. So therefore, they are logically equivalent to each other. Questions? All right. So if there are no more questions, then we can wrap up the tutorial here. I will be passing on the recording to Professor in case you guys need to revisit this recording. And I'll see you guys in the next tutorial. Just note as well. So if you guys have any questions for the next tutorial exercises, just make sure to email me those questions at least like 1 or 2 days before. And then I'll make sure to include it in the next tutorial. And that's everything for this tutorial, and I'll see you guys in the next one.
Sir.
Yep.
So I was working on I think it was 1.2, and I came across this question, and I'm having trouble with it. Can we go over it, or is there no time?
You can email me the question. Again, for the next exercises, just make sure to email me the question at least like 1 or 2 days before, okay?
Okay. Yeah, sure.
All right. Thank you, guys. And
I
yep,
have a question.
go ahead. Yeah.
For the next time, can we email even about the previous topics?
You can email me about the previous topics, but I might not cover it in the next tutorials because I am already running out of time for the upcoming exercises. So therefore, I might be able to reply you over email, but I cannot guarantee that.
Okay, thanks.
All right, but if you have any questions, just email me, and I will make sure to answer those if I can.
Okay, thank you.
All right, thank you guys. Take care and stay safe, and I'll see you guys in the next one.
Thank you, you too.
Thank you. Bye.
Bye.